The images started coming in and scientists went quiet. Not the excited, buzzing quiet of people who just saw something beautiful, the deep, unsettled quiet of people who just watched a textbook fall apart in front of their eyes. What the James Webb Space Telescope has been revealing, galaxy after galaxy, discovery after discovery, month after month, is not filling in the gaps in our understanding of the universe. It is tearing those gaps wide open. And the most alarming part is not any single discovery. It is the fact that the discoveries keep coming, and each one lands harder than the last. This is the story of how the most powerful telescope humanity has ever launched into space has spent the last few years quietly dismantling our best models of how the cosmos works, and what scientists are now scrambling to figure out. To understand why what James Webb is finding is so deeply shocking, you need to understand what scientists expected to see when it switched on in July 2022. For decades, cosmologists had built what they called the Standard Model of Cosmology, a precise, mathematically elegant framework describing how the universe began with the Big Bang 13.8 billion years ago, how it cooled and expanded, and how galaxies slowly, gradually assembled themselves over billions of years out of diffuse clouds of hydrogen and dark matter. This model was not a rough sketch. It was a detailed, refined blueprint built from decades of observations. Scientists were confident in it. And when James Webb, with its 6.5-meter gold-coated mirror collecting more than 6 times the light of the Hubble Space Telescope, seeing the universe in infrared wavelengths that cut through dust like it is not even there, when it finally opened its eyes and looked at the very early universe, scientists expected to see the blueprint confirmed. Instead, they saw something that one researcher described simply as, "It looks nothing like what we predicted." The first shock arrived almost immediately. In the early universe, in the first few hundred million years after the Big Bang, James Webb found galaxies, not faint, diffuse smudges struggling to form in the primordial dark. Bright, massive, surprisingly well-structured galaxies, blazing with star formation at a rate and intensity that had absolutely no business existing that early. These were not small things. Some of them contained stellar masses that should have taken billions of years to accumulate. And yet, there they were, fully assembled, shining intensely in a universe that was barely a few percent of its current age. The standard models of galaxy formation had predicted nothing like this. These objects were so out of place, so impossibly mature for their cosmic age, that researchers gave them a name that told you everything about how they felt: universe breakers. And then Webb broke its own record, repeatedly. In May 2025, the James Webb Space Telescope confirmed the most distant galaxy ever observed. Its name is MOMZ14. The light from this galaxy left its source just 280 million years after the Big Bang, meaning this galaxy existed when the universe was less than 2% of its current age, and MOMZ14 is not a faint ghost of a galaxy. It is bright enough that astronomers confirmed it could have been detected even if it had been 10 times dimmer. It emits light suggesting the presence of old stars, stars that must have formed, lived, and died even before this galaxy's light began its 13.5 billion year journey toward James Webb's mirror. The researchers studying it described a growing chasm between theory and observation. That chasm has been growing since Webb first opened its eyes, and MOMZ14 made it wider. But here's where the story goes from remarkable to genuinely unsettling. Because it is not just the distance records. It is what these early galaxies look like inside, scattered throughout James Webb's deep images of the early universe, tiny ruby-red pinpoints of light, seen everywhere Webb looks when it peers back to when the universe was only a few hundred million years old, is a class of object that nobody expected and nobody can fully explain. Astronomers call them little red dots, and the more they study them, the stranger they get. At first, scientists assumed these little red dots were simply very compact, very active young galaxies in the early universe, miniature powerhouses of star formation burning hot and red. That explanation felt uncomfortable but manageable. Then the spectra came back, the detailed light fingerprints that reveal what these objects are actually made of and how they are moving. And the uncomfortable became extraordinary. The data showed these objects had atmospheres, not like galaxies have atmospheres, like stars have atmospheres. Dense, turbulent envelopes of superheated gas surrounding a single central engine, rather than the spread-out stellar populations you would expect from a galaxy. In September 2025, a team of researchers published findings suggesting that little red dots may represent an entirely new class of cosmic object, one that has never existed in the universe since this early epoch and has never been seen before. They proposed these objects might be what scientists now tentatively call black hole stars, colossal spheres of dense, hot gas that look superficially like enormous stellar atmospheres. But at their hearts, instead of nuclear fusion powering them the way fusion powers a normal star, there is a supermassive black hole consuming surrounding matter and blasting out energy. The night sky of such a galaxy, one researcher said, would be dazzlingly bright, lit not by millions of separate stars, but by one inconceivably powerful central engine wrapped in a glowing cocoon of gas. And then, around 2 billion years into the universe's history, these objects vanish. They simply disappear from Webb's view as suddenly and inexplicably as they appeared. As of early 2026, X-ray data from the Chandra Observatory has provided the first evidence supporting the black hole star interpretation, with one little red dot found to be emitting X-rays in a way consistent with a deeply buried, furiously feeding, supermassive black hole. The lead researcher on that study described it as what may let us connect all the dots. The question of what these objects are is still open, but whatever they are something new, something that textbooks do not contain. And if all of that were not enough, James Webb then walked up to one of the most fundamental measurements in all of physics and confirmed that it is broken. The number that defines how fast the universe is expanding is called the Hubble constant. It describes, in kilometers per second per megaparsec, how quickly galaxies are flying apart from each other as the fabric of space stretches. Getting this number right is not merely academic, it is foundational. The Hubble constant determines our entire timeline for cosmic history, our understanding of dark energy, and our predictions for the ultimate fate of the universe. For years, two completely independent methods of measuring the Hubble constant kept coming up with different answers. The first method looks at the cosmic microwave background, the faint afterglow of the Big Bang itself, the oldest light in the universe, and extrapolates forward using our best physics to predict what the expansion rate should be today. That method gives a value of approximately 67 kilometers per second per megaparsec. The second method uses a cosmic distance ladder, measuring the distances to nearby galaxies using pulsating stars called Cepheids and exploding stars called supernovae, and directly clocks the expansion rate as it is happening right now. That method consistently produces a value closer to 74 kilometers per second per megaparsec. 7 kilometers per second per megaparsec might not sound like much, but these are two of the most rigorous measurement campaigns in the history of science, and they disagree. That disagreement, called the Hubble tension, has kept cosmologists awake for years, with many hoping it was simply a calibration error, some subtle bias in how Hubble's instruments measured those distance ladder stars. So when James Webb came online, one of its first major jobs was to check the math, to measure the same Cepheid stars and type Ia supernovae with its vastly superior infrared instruments, free from the calibration uncertainties that had always haunted Hubble. And what it found, confirmed across years of observations and published in the Astrophysical Journal by Nobel laureate Adam Rees and his team at Johns Hopkins, was unambiguous. Webb's measurements matched Hubble's local expansion rate perfectly. The tension is real. It is not a measurement error. It is not a calibration artifact. The universe genuinely appears to be expanding faster right now than our best physics says it should be. As Rees stated plainly, our understanding of the universe may be incomplete. Something is missing. Either there is a new cosmic ingredient, possibly a form of early dark energy that gave the universe an unexpected kick in its first moments, or our equations of gravity on the largest scales are somehow wrong, or there is exotic physics that no one has yet described. Nobel Prize-winning cosmologist David Gross has called it a crisis. The James Webb Space Telescope did not solve this crisis. It confirmed, with higher precision than ever before, that the crisis is absolutely real. As if the early universe were not busy enough dismantling cosmological models, James Webb has simultaneously been tearing into questions about life itself. The telescope was designed, in part, to study the atmospheres of planets orbiting other stars, and its capabilities in this domain have already produced results that were thought to be decades away. In the TRAPPIST-1 system, a compact family of 7 Earth-sized rocky planets orbiting an ultra-cool dwarf star just 39 light-years away, Webb has been systematically testing each world for signs of an atmosphere. The results have been simultaneously sobering and encouraging. TRAPPIST-1c and TRAPPIST-1d, 2 of the planets in or near the habitable zone of their star, show no evidence of a thick, Earth-like atmosphere. For planetary scientists, that is important information. Not every rocky planet in a habitable zone automatically has the conditions for life, but the campaign continues. And elsewhere, Webb has already proven its ability to detect carbon dioxide, water vapor, sulfur dioxide, and other complex molecules in the atmospheres of planets orbiting other stars, doing in a single observation what would have taken decades of Hubble time, if it could have been done at all. The organic chemistry discoveries coming from Webb go even further. In November 2025, astronomers announced that Webb had detected a trove of complex organic molecules, including benzene and methane, frozen in ice around a young star in the Large Magellanic Cloud, one of the Milky Way's neighboring galaxies. These are the kinds of molecules that are considered precursors to life. Finding them in another galaxy, around a star that is in the earliest stages of forming a solar system, tells scientists that the raw chemical ingredients for life are not uniquely abundant in our own cosmic neighborhood. They appear to be spread widely across at least this corner of the universe. And then, going even further, Webb's deep observations have also found organic molecules unexpectedly concentrated in the dusty core of a galaxy millions of light years away, including the methyl radical, a highly reactive carbon-bearing molecule never before detected outside the Milky Way. The cosmos, it turns out, is steeped in chemistry. Complex, carbon-rich, life-relevant chemistry in places no one thought to look for it. And just when you think the parade of surprises might slow down, James Webb spotted something in 2026 that left astrophysicists reaching for words. An explosion so bizarre, so defiant of every known category, that the best explanation anyone could offer was that it represents something science has not named yet. Designated GRB 250702b, this event was detected on July 2, 2025, and immediately flagged as deeply unusual. Gamma ray bursts, the most energetic explosions in the universe, typically last between a fraction of a second and a few minutes before fading. GRB 250702b lasted 7 hours. 7 hours of repeated outbursts, blasting narrow jets of particles at nearly the speed of light, far outlasting any known physical process that produces gamma ray bursts. Follow-up observations from James Webb revealed the explosion occurred inside a massive, extremely dusty galaxy approximately 8 billion light-years away, meaning this event took place long before our solar system even formed. What caused it remains genuinely unknown. It does not match the collapse of a massive star. It does not match the merger of two neutron stars. It does not fit any established physical model for what produces a gamma ray burst. The paper describing it, published in early 2026, used a phrase you almost never see in scientific literature outside of this telescope's era. It defies known physics. That phrase, defies known physics, has been appearing with uncomfortable regularity in papers built on James Webb data, not as dramatic exaggeration, as a factual description of the gap between what the telescope observes and what current models can explain. There's a pattern here that runs through every one of these discoveries. The James Webb Space Telescope was built to test our understanding of the universe at its deepest and most extreme. And what it found is that our understanding at those depths and extremes is fundamentally incomplete. The early universe grew up far too fast. The objects populating it include at least one entirely new class of cosmic thing that nobody predicted. The universe is expanding faster than physics says it should. Organic chemistry is woven through the cosmos on scales nobody anticipated, and cosmic explosions are occurring that no existing physics can explain. This does not mean science is broken. It means science is working exactly as it is supposed to. Every time humanity has built a more powerful eye, every time we have looked deeper, clearer, and further than before, the universe has responded by showing us something we did not know to look for. James Webb is not the end of that story. It is the most dramatic chapter of it so far. The discoveries will keep coming. The models will keep being revised. And somewhere in the data arriving right now, in the terabytes of infrared light that James Webb is capturing tonight, 1.5 million kilometers from Earth, in the cold and silent dark, something new is waiting. Something that will require us to rewrite the textbooks again.